Hello everyone, you are welcome to today's lesson. Excuse me, we are going to continue from where we stopped. In our last class, we were able to provide for the span reinforcement. Today we are going to continue with the continuous edge. You always prepare your calculation sheet like this. Then you bring back your UDL because you are now calculating for the moment at the continuous edge of the short span. The UDL was 14.52 kilonewton per meter run. All right. Then our moment coefficient was equals to, for the positive moment it was 0.042. Then for the negative moment it was 0.056. For those just joining us, please go to the previous videos I made. One of the classes, you find out how we're able to get the moment coefficients for this particular panel. Then we have the span to be equal to 4.1125 meters. Right. Now what we'll do next now is to calculate for the moments of the moment, continuous edge moment. So you cannot put here continuous edge. Continuous edge. Continuous edge. Alright. So you moment is equals to 0.56 multiplied by 14.52 multiplied by 4.112 square. This one will give me, if you compute, calculator, you compute, you're going to have 0.056 multiplied by 40.52 multiplied by 4.1125 square. This one will give me 13.75 kilonewton meters. So you convert to kilonewton per millimeter, or convert to you convert to newton millimeter, you're going to have 13.75 exponential 6 newton millimeter per millimeter run. All right, that's for the value of your m. After getting your m, these are the stages you follow. These are the steps you take. After getting your m, you calculate for your k. If you also want to get the value for your k, of the k, you go to one of the classes where when we taught all this. So the k is equal to moment, which is equal to 13.75 exponential 6 over SEU, which is concrete cover, multiplied by B, which is always 1000, multiplied by 124, which is our effective D, all squared. Alright. So we have this is less or equal to 0.156. Okay. So when we compute this, we are going to have 13.75 exponential 6 divided by 20 multiplied by 1000 multiplied by 124 square. We are going to have 0.045. K is 0.045 this is less than this, so you make use of the lesser value. Alright, make use of the lesser value of 0.045. Then the next step, you calculate for your LA. LA is what? LA is equal to 0.5 plus square root of 0.25 minus K. Our K 0.05, 0.045 over 0.9, which is a constant. So if you solve for this again, we are going to have 0.25 minus square of 0.25 minus 0.045 divide 0.9. This one will give me 0.45. Okay, 0.45. And if you add 0.45, this equals to 0. This must be less than or equal to 0.95. Alright, so 0.5 plus 0.45 will give me equals to 0.95. So see, you can see the conditions. LA must be less than or equal to 0.95. So this one is equal to 0.95. Use 0.95. Assuming the value we got from this computation was 0.8, you use 0.8. So you use a lesser value. Alright. So now we will now move to calculating for our Z. What is our Z? Our Z is equal to LA multiplied by D. This is equals to 0.95 multiplied by 124. This is equals to, if you compute that again, we are going to have 0.95 multiplied by 124. This one will give me 117.8. 117.8 millimeters. Alright. Then the next step is to calculate for our AS. Our AS is equals to, this is the area required. You know, the area of steel required for this structure to be okay. Alright, so the area of steel required is equal to M, our moment, that's 13.75 exponential 6 over 0.95, the constant, multiplied by Fy, this is our characteristic strength of steel, 14, multiplied by the Z, 117.8. Alright, this will give me, to compute this again, that will give me 13.75 exponential 6 divided by 0.95 multiplied by 14 multiplied by 117.8. This one will give me 299.67 millimeter square. Alright, so will not be our A. Now if you go to the area of steel in the DS code, the nearest area to be provided is supposed to be for Y12 at 300 millimeter center to center. The AS would have been supposed to be 377 millimeter square. Alright, but again, recall that in one of the classes I said the steel they produce in this country is not up to this standard size of steel. So I cannot provide for 12 mm at 300 center to center here. Alright, under standard setting, this is what you're supposed to do, because one of the objectives design is to reduce cost. The factor of safety shouldn't be too high, that the cost of actually constructing that building becomes too expensive with no advantage. So under standard setting, we are supposed to use this area, this 12 mm at 300 center to center. You see why we are talking about that cost of construction of building. 12 mm at 300 center to center would have been cheaper than when you provide for. Now, because of the standard nature of our materials, I'm providing 12 mm bars at 200 center to center top. And this area AS provided will be equal to 566 millimeters square. Alright? Because of the substandard nature of the steel we are producing in this country, we are now using 12 mm millimeter at 200 center to center. You see the cost we are talking about now. This reinforcement, this arrangement, this spacing will provide more 12 mm than this. Where we're supposed to, for instance, where we're supposed to use 10, 12 mm, for instance, 10, 12 mm, 10, 12 mm times, they will now be talking about using 15, 12 mm here. All right, so that is the area we're talking about. So practically, I'm going to provide after getting our A to this, I will now say provide Y12 mm diameter bar. All right, provide Y12. You can put the 12 diameter at 200 center to center top. Remember, I told you that at the continuous edge, the reinforcement is always at the top. All right, the reinforcement is always at the top. So you now write your AS. AS provided is equals to 566 millimeters. Assuming this is your calculation sheet, remember your calculation sheet will come like this. This is your output now. So you will now come to the output to say Y12 at 300, 200 center to center top. So that if you employ the services of a draftsman, the draftsman will know where to apply the 12 mm. Because in most companies, they use draftsman to detail their structure under the supervision of a structural engineer. So this is how to calculate for your continuous edge. Then in our next class, we'll go straight to the long span of that particular panel. Then after the long span, after designing for the long span, we check for deflection that long span. Then we'll now move to the continuous edge of that long span again. So the only difference between these calculations, the calculation for the mid span, the shorter span, is that the effective depth of the short span is D equals to H, which is 150 minus 20 concrete cover minus steel over 2. That's the steel. You want to have 124 millimeter. Then when you are now calculating for D in the long span, this now becomes your H. Your D in the long span now becomes your 124 minus 12, which is equals to 112 millimeters. So this is now going to be our new effective depth when we are calculating for the long span. All right. So this weekend we are going to the first lesson we are going to do this weekend is going to be live. All right, I'm going to introduce everybody to the software I talked about earlier, Quicksilver series. How to use it to analyze structure like this. This particular software design structure. What you need to do is to get your informations like the bearing capacity, your life load, your dead load. You include them there. Then the span. You do your design in the software. After doing your design in the software, there are all the parameters you need in structural design there in the software. So that's what we are going to introduce this weekend. So if you are interested, please, if you are interested, you join us on Sunday. Or as subsequently, I'm going to tell you the exact time we use on Sunday. So if you want to know more about structure, always follow my page. We are going to do, we are going to calculate them, we are going to analyze them from one stage to the other so that it's become, very, very simple for everyone to do. Structural design is actually very interesting. If you put your mind in it, you get it. So that is it for today. Call it a day today. I'll see you in our next class. God bless.